13 billion years ago, inflation, quantum fluctuations, and the birth and rapid expansion of the universe, which we can only hope to understand from the faintest remnants imbued in the cosmic landscape and our sky. But where did it all start? And how does it end? Dealing with death is difficult. It's a somber acceptance and the complete and utter annihilation of physical consciousness. The end of life. There's no turning back. Depending on who you ask, it's the only thing that's absolute. Maybe even the purpose of life. But if you ask me, this absolute is entangled with so many questions. Why are we here? How did we get here? Are we here forever? Georges Lemaitre has a good explanation for the first question. The Big Bang, and then life on Earth. We have Darwin for that. How about the last question? Are we here forever? Well, there are a few theories for this. One of the leading theories is the heat death. In class, we talk a lot about a tendency to equilibrium. What about the universe itself? The death of the universe by simply reaching an equilibrium.
So, why do we think the Big Freeze will occur anyways? And what are the general principles behind the theory? The Big Freeze will happen when the universe can no longer sustain an increase in entropy, or put simply, the universe reaches maximum entropy. We can use a few formulas and relations to explain how this would happen. The universe's entropy can be approximated by k times n, where k is a constant and n is the number of particles in the universe. N, the number of molecules, can be represented as the total energy of the system divided by the quantized energy in the system. What I mean by the quantized energy of the system is its individual energy each particle has. Particles lose energy by splitting and becoming smaller particles until they are too small to transform anymore. Since there is a definite minimum energy particles can have, or E quanta, it means that there is a maximum number of particles that can exist in our universe. And because entropy is directly proportional to the number of particles, this means there is a definite maximum entropy. Okay, so we know there is a definite maximum entropy, but why do we expect to ever reach that point? Well, if dark energy, which we will touch on later, is a positive cosmological constant, then the universe will continue to expand and increase its volume. As seen in the formula shown, which is a more accurate version of what we've seen previously, entropy is proportional to the natural log of volume. Therefore, if the volume of the universe keeps increasing, the entropy of the universe will keep increasing, until, eventually, the entropy will reach its maximum and the universe will experience the Big Freeze.
So how does entropy relate to heat death? So we may have heard that entropy of the universe is always increasing. In fact, many scientists refer to entropy as the arrow of time. This is because if we leave a system at rest, over time it will tend to become more disordered and spread out with its surroundings. But what does this mean in reality, this disorder? Well, let's take a system like a balloon filled with one gas. The disorder refers to the number of ways those gaseous particles can be arranged within that balloon to make up the same gaseous state. If we think about the difference between that balloon and something like a cube of ice, or a solid, there's only a certain amount of ways a solid can be arranged that it still obeys its crystalline structure to be a solid. Versus in a gas, the particles can be much more disordered and still become that gaseous state. The expansion of the universe is very similar in many ways to a balloon being allowed to release with its surroundings. If we think about that over time, there's more and more types of particles in the universe created, and they're allowed to expand and interact with one another or be in different arrangements, we can say that there's a higher disorder of the system over time. But what does this early universe look like? And how can we actually quantify the entropy over time? So it's very difficult to get an estimation of the entropy of the exact moment of the Big Bang, because the only energy that was the only particles that were present were in the form of pure energy and radiation. If we think about this universe, it had an average temperature of about 2 million Kelvin. So what if we look at the first moment that particles like electrons and leptons were formed? So that was about 10 to the negative 12 to 10 to the negative 6 seconds after the Big Bang. So we can calculate the number of these particles present by taking the mass of the universe and the mass of a single electron and get an estimation for how many of these particles were present. We get an estimation of about 11 times 10 to the 82 particles present in that very early stage of the universe. Now, if we jump forward to the first creation of particles like neutrons and protons, we can do the same calculation and figure out how many particles were present. So after we do that, we get about 6 times 10 to the 79 particles present. Now you're thinking, most of these particles are now that we see are in the form of atoms that create the solids around us. When was the first atom created and what did that look like? So about 380,000 years after the Big Bang, the first atom was created, which were hydrogen and helium atoms, hydrogen being the lightest of the two. We can actually calculate the number of these atoms present by using the molar mass. So if we take the mass of the universe divided by the molar mass, about 1.008 cubes, we can get the number of moles, and then once we multiply by Avogadro's constant, we get that there would be about 6 times 10 to the 76 hydrogen atoms present in that early universe, but still several years after the Big Bang. So seeing this, we can think about the fact that there's now more ways to arrange the particles, since there's electrons, protons, and hydrogen atoms, and then continuing on in the universe, the more complicated particles that are present, the more ways it can interact and have different microstates. But what is the entropy, and how can we quantify that? So like I said earlier, the earliest stages of the universe were almost pure radiation, and there was about 10 to the 88 particles present. If we take the equation for entropy, being S is equal to the Boltzmann constant times the ln of our microstates. And then if we factor in the account that 10 to the 88 is a much larger system, so we can use the approximation that entropy is approximately the Boltzmann constant times the number of particles present. We get that the entropy of the early universe will be about the order of 10 to the 88 Boltzmann constants, or about 1.38 times 10 to the 65 joules per Kelvin. So how has that evolved over time? Well, scientists consider the expansion of the universe to actually be isentropic, which is expanding with constant entropy due to the change of temperature and pressure and volume. However, how does that reconcile with the fact that the entropy of the universe is always increasing? Well, the answer is actually quite simple, and it's of black holes. We can see that in this table, the major factor causing all of the increase of entropy in the universe is black holes. But how do black holes actually have an increase in entropy? Well, it's because of the lost information from the absorption of particles in a black hole. So we actually get that the black hole's entropy, which is an equation found by Stephen Hawking, is proportional to the area of the event horizon of the black hole. And this makes sense because we can think of the larger the black hole is, the more particles it will absorb. So how does the universe end? And what does entropy look like at the very end of the universe? Well, if we look at the universe expanding over time, and the fact that black holes will increase in size and take in more and more matter, we can think of the end of the universe as being just black holes and some Hawking radiation exiting. So if we take, again, the mass of the universe and we plug it back into the entropy equation for black holes, we actually get an estimation of the final entropy of the universe, or maximum entropy of the universe. So when we do that, we get about 2.65 times 10 to the 22 Boltzmann constants, or 3.65 times 10 to the 99 joules per Kelvin. So we can see that at the very ends of the universe, entropy is increased significantly compared to the start of the universe from these black hole interactions.
The Friedmann equations, which model a homogeneous and isotropic universe, can give us some interesting insights into the fate of the universe. Most notably, they show the different phenomena that contribute to the expansion rate of the universe. This equation here relates the current expansion rate of the universe to current density values omega and the Hubble parameter h naught. It is found to be the sum of four terms relating to radiation density, matter density, spatial curvature density, and a cosmological constant, also sometimes called the vacuum density of the universe. This cosmological constant was first proposed by Einstein in 1917, which was many years later self-proclaimed as his biggest blunder. However, 40 years after his death, he was proven to be correct, as the constant was needed to properly describe the accelerating expansion of the universe. This constant is thought to be largely related to dark energy and will be crucial in describing the fate of our universe. The WAMP has recently taken measurements of cosmic background radiation that shows the spatial geometry of the universe to be also almost flat, not open or closed. This measurement lets us assume that the spatial curvature component of the previous Friedmann equation is zero. This leaves the radiation and matter densities, along with the cosmological constant, to describe the expansion of the universe. It is important to note that the matter density refers to both baronic or ordinary matter and dark matter. Current values of the Hubble universe expansion constant, radiation density, and matter density measured by the Planck cosmology probe can give an estimation for the cosmological constant from current measurements. This measurement of the cosmological constant leads to what is called the worst theoretical prediction in the history of physics by Hobson in his textbook General Relativity and Introduction for Physicists. This is because using most quantum field theories, the theoretically predicted value of the cosmological constant is found to be 120 orders of magnitude larger than the one that was measured. As of today, there is no known way to derive the cosmological constant using modern particle physics. This is obviously a very big problem and a major challenge that the theoretical particle astrophysics are looking to solve. So we sat down with Aaron Vincent, a leading theoretical particle astrophysicist at Queen's University, to ask him some questions about dark energy, the cosmological constant, and the end of the universe.
So we want to tackle the question of what is dark energy and why was it postulated, and then kind of the implications of what dark energy is.
So I think that the story depends how far back you want to go. The normal way the story is told is it starts with Einstein, who figured out general relativity, which is how gravity works in beyond what Newton had imagined. So the idea behind general relativity is that space-time is this sort of big fabric, and the presence of matter is curving space-time, while the curvature of space-time is affecting where matter goes. And then Einstein realized, well, I can apply this to not just a star going around the galaxy or a planet going around the solar system, I can apply it to the entire universe. And when he did this, he realized that the total amount of matter in the universe is making the universe actually change its size. And he looked out at the sky, asked astronomers, saying, well, is the universe expanding and contracting? And they said, no, well, it's more or less a steady state. So he took his equations, the Einstein equations, and added a piece to it called the cosmological constant, which was there to kind of stabilize things. But then very soon, Edwin Hubble and other astronomers realized that actually, no, the universe is expanding. And we don't need that dark energy component. It's in this state of expansion that seems consistent with just there being matter and there being some initial amount of density. And so Einstein called this his biggest blunder, to postulate the existence of this dark energy. We kind of removed the need for dark energy, and we went and, we being cosmologists that are not me, went and measured the expansion rate of the universe and looked at, well, how is it expanding given the amount of matter and the amount of radiation, because light contains energy and energy contributes to the overall density of stuff in the universe. And until the late 90s, we thought, well, we didn't need that cosmological constant of Einstein's. Until precision measurements of the expansion rate, the accelerated expansion rate of the universe, were made by astronomers looking at supernovae that were at very high redshifts, very large distances away from us, that told us that the expansion rate is actually accelerating, which is not consistent with what you would just predict if you only had ordinary matter or radiation. What the Friedmann equation says is the Hubble rate, so the expansion rate, is equal to some constants times the density. And the density of matter that's as the universe expands, that's getting diluted as 1 over the volume. So the space is expanding, but the number of things is going down. The number of things is constant, so therefore the number density is going down. Dark energy is very weird in that you're saying there's a constant energy density in a specific volume. And so if I double the amount of volume in the universe, but I keep the same energy density, then I've doubled the amount of energy in the universe. And that is what leads to an accelerated expansion rate.
Does this mean that there's some kind of ongoing research going on right now to find the magnitude of this dark energy constant?
Fundamentally, there's a large amount of vacuum energy that is just due to the presence of quantum fields and the uncertainty in those quantum fields that you can go and try to calculate on your own to get, and what you get is an energy density. And that energy density doesn't depend on how big the universe is. It doesn't know. It only knows locally what's going on. So that would behave like a cosmological constant, like dark energy. So this should be what we predict. This should be that dark energy that's making the universe expand. Except if you do the calculation, you get it wrong by about 120 orders of magnitude. You get an answer that is 10 to the 120 times too high.
So because we don't understand exactly what dark energy is, we're not certain that a specific value of the constant will lead to a certain end of the universe.
Yeah. So based on what we know, based on what we've observed, under the hypothesis that it is indeed dark energy, then we have a pretty good idea of what's going to happen. It's not very pretty, but at least it's going to take a while before we get there.
And given that this is explained all by dark energy, would you then be able to say the heat death of the universe would occur or the big crunch would occur based on the acceleration of the universe?
Right. So based on what we know now, there seems to be a dark energy component, and as I said, that matter component, which is kind of keeping us from expanding too fast, well, that's getting diluted away from the expansion of the universe. We see that from galaxies flying away from each other. The radiation component, which is the cosmic microwave background, that's also being diluted away and becoming lower and lower in temperature. So what we're going to be left with in about 150 billion years is more or less just dark energy, and as things slowly they'll start to expand faster and faster away from us, and they'll be receding away faster than the light coming from them can catch up. So it will look like they're receding faster than the speed of light, and that means that we'll lose causal contact with these galaxies.
As Professor Vincent mentioned, there's ongoing research as to what dark energy is and whether it is the cosmological constant causing our universe to expand, as quantum field theory suggests. Now, if this is true, and dark energy is a positive constant throughout time, we know the universe will expand rapidly until it reaches the point of maximum entropy. This is where all the black holes will engulf all the matter that once existed in the universe, causing nothing in our universe to exist except these black holes and a frozen abyss of nothingness.
I'd like to take this opportunity to thank all of our sponsors and contributors. Firstly, Aaron Vincent, for letting us use his office and expertise on the subject matter. Additionally, Subway for sponsoring the production of this documentary. Subway, eat fresh. Thanks for watching.